Let's get right into it. Today, we're putting on our senior biomaterials investigator hats to dissect a framework that is literally rewriting the rules of biomedical engineering. We're looking at the quantum synovia metalube, or QSM system. This is an original quantum-to-macroscopic biomimetic framework developed by researcher Lázaro López Paz. What we are exploring in this explainer is how to bridge complex quantum mechanics with advanced laboratory synthesis to completely rethink how we treat osteoarthritis and joint degradation. Here is our roadmap for today. We'll start with viscosupplementation versus the QSM system, then dive into the DFT methodology and the QHE factor, followed by automated analysis with Python. After that, we'll cover the chemical synthesis protocol, experimental design and optimization, and finally wrap up with tribological testing and clinical efficacy. All right, Section 1, viscosupplementation versus the QSM system. To understand why QSM is such a game changer, we have to look at the current clinical standard. Traditional viscosupplements, like standard hyaluronic acid, are basically biological band-aids. They give temporary relief, sure, but they suffer from rapid enzymatic degradation and completely fail to actively promote tissue regeneration. The QSM system, on the other hand, treats the joint as a dynamic engineering challenge. It relies on a covalent siloxane crosslink on high molecular weight hyaluronic acid. This specific chemical logic creates an adaptive mechanical metamaterial. So, under the immense crushing loads of a human joint, it actually exhibits a negative Poisson's ratio. That means it expands laterally to distribute stress, deploying quantum hydration shells to actively protect and regenerate the cartilage.
Let's move down to Section 2, DFT methodology and the QHE factor.
To engineer a material this advanced, we start at the absolute molecular level with density functional theory, or DFT. For any senior investigators looking to reproduce these quantum simulations in your own high-performance computing clusters, consider this your master cheat sheet. You must strictly adhere to these exact computational parameters. We're using the B3LYP hybrid functional, but crucially incorporating Grimmie's D3BJ dispersion correction. You absolutely need that to capture the van der Waals forces and hydrogen bonding in the hydration layers. You'll run this using a 631G DP base set, scaling up to def2TZVP for fine energy calculations, all within an SMD water solvation model at a physiological 310 Kelvin. These are your validation parameters for software like Gaussian 16 or Orca.
Using those parameters, we achieve a massive covalent stability of -55.2 kilocalories per mole for the siloxane crosslink. But the real driver of the hydrogel's tribological efficiency, its ultimate lubricity, is the HOMO-LUMO gap. It clocks in at exactly 3.21 electron volts. That 3.21 EV isn't just a random number. It is the absolute sweet spot for optimal dynamic polarizability. It proves exactly how the electron cloud will flawlessly shift and respond under the shear stress of a moving joint to maintain a totally frictionless surface.
The crucial mathematical link predicting this behavior under immense pressure is the QHE factor, or quantum hydration enhancement. Here's the mathematical logic. You take the absolute value of the hydration stabilization energy, which is 18.7 kilocalories per mole, divided by 10 and multiply it by the HOMO-LUMO gap, divided by 3. We are targeting a QHE score between 6.8 and 7.2. Hitting that exact metric is the holy grail because it mathematically guarantees a final friction coefficient lower than 0.005.
Moving right along to Section 3, automated analysis with Python.
Let's be honest, running these quantum calculations produces massive amounts of data, and nobody wants to manually parse thousands of lines of Gaussian log files. That's where this custom Python script comes in. Think of this as a quick, technical tutorial for automating your lab simulations. Instead of tedious manual data entry, the script uses a universal cclib parser with a regex fallback to instantly read output files. It automatically extracts your binding energies, calculates that critical QHE factor we just broke down, and instantly generates structured JSON and CSV files alongside professional 300 DPI graphs. It's essentially your automated lab assistant, flawlessly bridging the gap between raw quantum data and actionable laboratory insights.
Up next, Section 4, Chemical Synthesis Protocol. With the digital simulations validated and automatically analyzed, let's step into the physical lab for the GMP-compatible chemical synthesis. For biomedical researchers, this is your practical 5-step protocol to yield 100 milliliters of a highly stable, sterile 3% hydrogel ready for in vitro testing. Step 1. Activate the hyaluronic acid using EDC and NHS in a sterile PBS buffer. Step 2, siloxane grafting, which requires 4 to 6 hours of agitation at exactly 37 degrees Celsius. Step 3 is smart doping via controlled sonication. Step 4, adjust the pH to exactly 7.4 for gelation. And finally, Step 5, purify the matrix with a 24 to 48-hour dialysis and a 0.22 micrometer sterile filtration.
I want to highlight the chemical logic of that smart doping in Step 3. The dopants we introduce aren't random. Magnesium ions, which show a massive adsorption energy of minus 42.3 kilocalories per mole, actively promote cellular in vitro regeneration, specifically chondrogenesis, or cartilage tissue formation. Meanwhile, the iron oxide nanoparticles provide essential mechanical reinforcement and a magnetic response. Together, they lock the metamaterial's structure into place so it survives extreme physical stress.
Section 5. Experimental design and optimization. Before we even think about clinical applications, the final chemical formulation has to be statistically perfected. To do this efficiently, the framework uses a fractional factorial experimental design, specifically a 2 to the power of 5 minus 1 resolution. This setup is brilliant because it prevents us from having to run thousands of redundant, expensive lab tests while still isolating the critical variables. You balance 5 factors: percentage of hyaluronic acid, the siloxane to HA ratio, concentrations of magnesium and iron oxide, and the gelation type. By statistically mapping these interactions, researchers pinpoint the exact chemical ratios needed to hit our targets, a QHE factor above 6.5, and crucially, a storage modulus, or G', greater than 600 pascals to guarantee robust mechanical stability.
Finally, Section 6, Tribological Testing and Clinical Efficacy.
The final hurdle for the optimized QSM hydrogel is surviving extreme physical stress in tribological testing to prove its clinical impact. We use a ball-on-flat tribometer set to 37 degrees Celsius against fresh bovine cartilage. We subject the hydrogel to loads equating to up to 10 megapascals of pressure. That is an immense, bone-crushing amount of force where traditional supplements instantly fail. But remember our metamaterial design? Under this 10 MPa load, the QSM system doesn't just squeeze out. Its negative Poisson's ratio forces it to adapt, while the quantum hydration shells withstand the shear, actively restoring joint lubrication.
The ultimate acceptance criteria for QSM in these extreme lab tests is achieving a friction coefficient lower than 0.005. That is the magic number, mathematically predicted by our QHE factor calculation. And amazingly, achieving a friction coefficient of 0.005 is a level of lubrication that actually surpasses natural, healthy human cartilage.
This whole framework, from mapping quantum electron gaps to Python automation and practical GMP lab synthesis, forces us to ask a profound question. As we seamlessly blend quantum physics with biomedical engineering to create materials that literally outperform nature itself, how quickly will these regenerative metamaterials become the new gold standard in clinical care? Are we witnessing the end of invasive joint replacements? Consider that as you look to the future of our field.